Good morning, everyone, and welcome to our first of 4 videos on the gross anatomy of the muscular system. In this lecture series, we're going to actually be approaching the muscular system in a completely different way than we do in lab. So in lab, we're focused on learning where these muscles are, what they do, and how they attach to the skeletal system. In lecture, we're actually going to be focusing a lot on biomechanics, how the muscles work together as a group, and then looking at the why. Why are we learning where these muscles are? Who's clinically relevant? And by learning a lot of these orientations, I'm going to be helping you guys out with your lab, like understanding where flexors are located or common attachment sites, common actions. So they're together, but you're not expected to know the same level of content. So that being said, let's get started with our first lecture on the biomechanics of muscles. Now, I know this sounds scary, but for everyone heading into physical therapy, the physics of how muscles act on joints is really important because it lets us understand why certain muscle groups can lift heavier objects and others can't, and how we can utilize that to our benefit to help with rehabilitation of our patients. For my nurses, this is important because one of the things you're going to be doing as a nurse, no matter where you are in the hospital, you're going to be moving patients. And it's really helpful to understand fulcrum, load, effort so that you don't hurt yourself when you have to turn a patient or move them from a bed to another bed or to a wheelchair, etc. So let's get started. Now, the first thing we want to talk about are the muscle attachment sites. Now, this is going to be important information for our lab as well. So muscles are going to create, one second. Muscles are going to create movement by crossing a joint. Okay, and we're going to get into all that as we get into the various regions of the body. But they have to cross the joint, and then the muscle will shorten, and that will create some sort of an action. So how the muscle attaches, it's going to attach to one end, and that's going to attach at another end. And you can cross one joint or two joints. Now, the attachment site that is on the bone that doesn't move, we call the origin, okay? The attachment site on the bone that does move is called the insertion. So I'm going to use an example. This is the one I'm going to use a lot because it's one we're all familiar with, which is your biceps brachii, okay? Now, the origin site for my bicep, sorry, it keeps blurring out. It's bicep, so it has two attachment sites up here in my scapula. That's the origin. The main action of your biceps brachii is to flex your elbow, okay? So when I'm flexing my elbow, notice my shoulder isn't moving, okay? The bicep, as we'll learn in lab, it has a few other actions as well, but the main action is this elbow flexion. So the origin, the attachment sites appear on the stationary bone. That's the origin. And then the attachment site on the bone that moves, in this case, it's on the radial tuberosity of my radius. When I flex my forearm, it's my radius that's moving, so that would be considered the insertion site. And then the action is just whatever happens to the joint when that muscle shortens. So those are some important terminologies. So here's an example, two very important ones. So again, we're going to have our bicep, which is the one we just talked about. So again, the origin of the bicep is up here in our scapula. It's bicipital, so it has two attachment sites. And here's the muscle belly. Here is the insertion site. Because when this muscle contracts and shortens, like we talked about in chapter 10, it's going to pull on this radius and decrease the angle of the joint, which is what we call flexion. Now, if we look down here at our calf muscle, this is your gastrocnemius, okay? It actually originates up here on the back of the femur, and it inserts down here onto the calcaneus. So when this muscle contracts, it's actually going to pull up on the heel bone, like this, which basically causes you to stand up on your toes. Okay, that's plantar flexion, if you recall from our discussion of articulations. So origin is up here, insertion is down here. One thing you're going to notice, two things. Notice this. The insertion is always distal. The origin is always proximal. Now, you guys know by now, when I say always, I mean 99% of the time. There's always going to be exceptions to the rule, but pretty much always, the insertion is distal from the attachment site and the origin is going to be proximal. The other thing you're going to notice is we always like to say the insertion moves towards the origin. So if we use the calcaneus for an example, it's going to elevate up and get closer to those femoral condyles. So the insertion moves to the origin. Why am I telling you this? When we get into lab, we are learning not all of our origins and insertions, but a good chunk of them. And if I ask you that on an assessment, knowing who's distal and who's proximal could really help you out in a pinch of like, shoot, I know it attaches at these two places, but I forgot who's the insertion and who's the origin. It's also really helpful in case you forget an action. So if you know the calcaneus is going to move up and go closer to the femur, you can do that action and go, oh my God, it's pointing my toes. It's plantar flexion. So understanding the attachment sites helps you a lot with the muscles content that we're going to be learning in lab. Now, what we're going to be talking about today primarily is lever systems. This is a lot of physics, but before you panic after you go onto Google and start looking this up some more, we're not learning any math. We're not calculating load or resistance. We're not calculating effort. We're not looking at torque. We're just understanding the arrangement of three components to a lever system, because this arrangement is how all of our muscles are arranged. And depending on orientation, we're going to get some different outcomes when it comes to the muscle movement. So the three major components we have our effort, we have our load, and we have our fulcrum. And as you can see, you can put them in many different ways, and those give us our first, second, and third class lever systems. Now, what is the effort? In terms of the human body, the effort, this is what's creating movement. So for our purposes, this is your muscle. That's what's causing the action. The fulcrum is the joint. This is what the muscle is crossing and it's pulling on to create that action. And then the load or the resistance is basically just whatever we're moving. So I'll just put what we move. Now, this could just be body part if we're talking in very general, like your hand, your forearm. I'll also be using some examples from like strength training, so like when you're lifting barbells and things like that, that's what you're trying to move. Now, as you can see, we have different orientations. We do need to understand who's a first class lever system. Do they provide mechanical advantage or disadvantage? What is the orientation of the effort, fulcrum, and load? And can you give me an example? So to help you remember the orientation, we are going to use 1, 2, 3, F, L, E. And what that does is it lets us know that first class lever systems have the fulcrum in the middle. So we can see that right here. Second class lever systems have the load in the middle, which again, you can see that right here. And then third class lever systems have the effort in the middle. So 1, 2, 3, FLE is going to help you remember those orientations for each one of the lever systems. Now, as I mentioned, when we're talking about these effort, fulcrum, and load, it all is really important because the orientation lets us know, are we going to have what's called mechanical advantage or disadvantage? So how we calculate this, and again, you can do this with actual math. For us, it's very subjective. We are looking at the distance between the effort arm and the load arm. What is the effort arm? What is the load arm? The effort arm is simply the distance between the effort and the fulcrum, and the load arm is the distance between the load and the fulcrum. We're going to go through in this same example after we've gone through all of our lever systems, but here's an example. This is for a wheelbarrow. We have our effort here, which is you lifting, goes all the way across. Here's our load. Okay, so the load is what's in the wheelbarrow itself, and then you'd have the fulcrum, right here in the middle, the pivot point, as it were. Okay, this is not drawn to scale, but for our purposes, you can see here, effort arm is going to be short, and then here you can see the load arm. Again, this is not to scale, so I can't really explain how this is a mechanical advantage, but this is just to illustrate what we mean by load arm and effort arm. And this is just to help you with that understanding of what we mean by mechanical and advantage and disadvantage. So when you have a mechanical advantage, the load is closer to the fulcrum and the effort is further from the fulcrum. So let me try to draw this more accurately. Here's our little line here. We're going to draw the wheelbarrow, but to more accurate standards. So the load here is going to be much closer to the fulcrum, and the effort is further away. So remember, here's your little wheelbarrow. There's the load, and then you can have like the little fulcrum point here. Okay, I can draw anatomical parts. I can't draw anything else. So this is a wheelbarrow. I put that on the wrong side, didn't I? It goes over here. So here's my effort. That's me lifting the wheelbarrow. My load is in here, and then the fulcrum point is like that angling point as you're lifting it. So because the fulcrum is closer to the load, you can see that here, this provides mechanical advantage. The effort is further away. What do we even mean by that? So when we talk about mechanical advantage, what it means is you can put in a lot less effort to lift something heavy, okay? If you orient your effort, your fulcrum, and your load into this orientation where the fulcrum is closer to the load, you don't have to put in a lot of effort to lift something heavy. It's the same idea if you've ever done any excavation in your yard and found a big boulder, and you get the big metal pole and you kind of create that fulcrum to help pull and dislodge the rock. The closer that fulcrum is to that big heavy rock, the less work you're actually going to be doing. Okay, so mechanical advantage lets us lift heavier things, but with less effort, but we don't have quite a bit of range of motion. So if you've used a wheelbarrow, you know I really only can lift the wheelbarrow maybe a foot off the ground. That's like the range of motion that I have. So the thing that we lose when we're in mechanical advantage is range of motion, distance to move, but we gain the ability to lift stuff really heavy. Now, mechanical disadvantage is the opposite. So now we're going to look at something else. We're going to look at our essentially like a shovel. So here is the handle of my shovel. Here's the arm of my shovel, and then that's the spade part. Okay. So in this case, the fulcrum is here. Your effort is going to be, make it kind of semi within reason, and then there's your load. So the effort to fulcrum is this distance. It keeps disappearing, and then you can see my load arm is much bigger. So now the load arm is much bigger than the effort arm. So what happens with mechanical disadvantage? With mechanical disadvantage, the first thing I want to say is we always hear the word disadvantage and we put a negative connotation to it, like, oh, it's bad. That's not what we mean here. It's just the opposite effect. So it's not bad, it's just another way of doing something. So this is how most of the muscles in our body are actually oriented in this sort of mechanical disadvantage state. We have to put in more effort to move a load. So if you've done any amount of yard work, know you can move a lot more on a wheelbarrow and be less tired than if you had to move that same amount of dirt with a shovel. Because it takes a lot more effort to move the same amount of dirt over time with a shovel because of the effort and the load orientation. Okay? The thing that we get with a shovel that we don't have with a wheelbarrow is I can move things further. I have a much bigger range of motion and I can do it faster. So it's more explosive in terms of speed and I get a lot more range of motion. So that's what you get with your biceps brachii versus say your calf, okay? So your calf is actually what we call a second class lever system, and it is in mechanical advantage. That's why when you stand on your tiptoes, it's so easy to move your entire body weight, okay? Then if you were to take that same amount of weight and try to do a bicep curl. Even though you're probably equally strong, maybe you can do like 50 or 60 pound bicep curls, right? But you're always going to be able to lift more weight with your legs than you are with your arms with a different amount of effort. So it's going to be a lot easier to do it with your legs. You can still move that weight if you've trained with your arm, but you're going to have to like really put in the effort to move that same amount of weight. But the difference is I can get a lot more movement and it's faster when I am using my biceps, which is the third class lever system, which always acts in mechanical disadvantage. So hopefully that stuck just a little bit. We're going to have an activity to apply this knowledge and assess different orientations in lecture next week. So don't worry, we're going to practice this. So let's go through our lever system. So the first one we're going to look at is our first class lever system. Now again, 1, 2, 3, FLE. In this case, the fulcrum in a first class lever system is in the middle. This is our atlanto-occipital joint, okay? The effort for the example that we're looking at our posterior neck muscles, and the load is just like your face, your skull, okay? The interesting thing about first class lever systems, besides the fact that they're very rare, is that they can either have mechanical advantage or disadvantage. It truly depends on the orientation and the ratio of the effort arm to the load arm, okay? So what did we just talk about? We just said that if the effort arm is shorter than the load arm, we'll have mechanical disadvantage, okay? That's what we see with the triceps brachii. So again, if we go back here to our elbow joint, this is the insertion side of my tricep. Here's my effort. My origin is kind of all up here because it's 3 heads. But the connection to the fulcrum is much smaller. So this action of extension is actually mechanical disadvantage, okay? And then if we look at the head, this is actually mechanical advantage because the load arm is actually, it doesn't show very well with this diagram, but the load arm is shorter than the effort arm. So I'm not really going to make you understand that or try to like apply it too much, but it's really just understanding that unlike the other lever systems we have, first class lever could be mechanical advantage or disadvantage. It just depends on the orientation and that effort arm load arm ratio. Now, second class lever systems we just talked about, right? When we're going through mechanical advantage. This is 1, 2, 3, FLE. Load is in the middle. So again, effort is our gastrocnemius. Load is at this sort of ankle joint, and then the fulcrum point is going to be your toes here. So as your calcaneus lifts up because your gastroc contracts, you're going to pivot on the balls of your feet and move your entire body weight, okay? Again, because the effort arm is longer than the load arm, we are going to have mechanical advantage. I can lift heavier things. I have a little bit less range of motion, okay? But I can lift the heavy things with less effort. It's a lot easier to stand on my tiptoes with my body weight than it is to try to curl my body weight. Now for third class lever systems, we have FEL. So 1, 2, 3, FLE, effort is in the middle. So the fulcrum of this particular example is your elbow joint. The effort is the bicep, so it's in the middle, and then the load is whatever your hands are holding, okay? So because the effort arm is shorter than the load arm, we can see that here, we have mechanical disadvantage. So it's going to take more effort to lift something heavy, but I'm faster and I have more range of motion, okay? So in terms of what do we need to know for these lever systems, I need to understand the orientation of the fulcrum, effort, and load. I need to know an example. I need to know, in that example, who is the effort, fulcrum, and load, and I need to know, do they operate at a mechanical advantage or disadvantage or both? That's what we need to know. So a couple things we want to talk about before we end this chapter and start actually looking at muscle groups. When you're looking at your muscle models and these diagrams, what you're going to see are a bunch of different shaped muscles. Okay, so we're going to have muscles that are circular, like this, that have like these rings running around it. We also have convergent muscles, like your pectoralis major. You're going to see all these lines on them. Those lines are actually the fascicles. Remember, those are the bundles of muscle fibers. And depending on how those fascicles are arranged, you are going to get different shaped muscles. And why would we have different shaped muscles? They're going to have different roles in the body. So for example, a parallel muscle, like the ones we're going to see in our neck in the next video, they're very long and strappy, and they all want in one direction. And because they're long and strappy, we can get a lot more movement out of them. Something like a circular pattern in your orbicularis oris, for example, or your orbicularis oculi, or even a sphincter muscle inside your GI tract, those are circular. So they basically change the opening, the shape of an opening, open or close, okay? So I'll let you guys read this, because if I sit here and tell you that, you're going to be bored out of your mind. But these are just definitions to help you understand why we have muscles built the way they do. So as you start learning their actions, you're going to go, oh, that makes sense. Why that is a circular muscle, why that is multipennate versus bipennate versus unipennate. Okay, so those are some examples for your fascicle arrangements. Now, the last things we want to talk about are how muscles are working together as a group. So one of the things that again, we're going to be learning in lab is that here's a muscle and this is what it does. But what you're going to find is that, wow, there's a lot of different muscles that are going to, for example, flex the forearm, or extend the arm, extend the neck, or internal rotation of the arm, or flex the hip. So it's really important to understand that a lot of the actions that we're learning are not by a single muscle. Some are, but not all of them. So we have lots of muscles that need to be activated to perform different types of movements. Now, the first two arrangements I want to talk about are a pair of muscles called a prime mover or agonist and an antagonist. So in this relationship, you're going to have one muscle that will activate and one muscle that will, in that moment, relax to perform the action. So back to our bicep. If I want to flex my elbow, okay, in this state, my triceps are activated because my elbow is extended. But now I want to flex it. If I try to contract my bicep while my triceps are contracted, there's no movement. You guys can try it right now. There's literally no movement. I need to let my triceps relax, and then I can start to bend at the elbow. So one relaxes, one contracts. Let's do the opposite direction. This guy's going to relax, this one will contract, and now I get extension. And you're going to see the same thing in your quadriceps and hamstrings. So the quadriceps are on the anterior surface of your thigh. They will contract to straighten your leg, and then the hamstrings will relax. And then when the hamstrings contract and the quads relax, that's how you're going to get that bending of your knee. And we'll go over, we'll talk, hint, spoiler alert, we'll go through hamstring tears and why those happen in our last video. Now, the other pairs of muscles that we want to look at, are types of muscles, are synergists and fixators. Now, sometimes you'll see them all grouped together as like they're just synergists, but this one has a fixator action. I like to separate them. So a synergist is basically, the dictionary definition is it's going to stabilize intermediate joints, but really what it's doing is it's really helping the agonist perform its action. So it's like an assistant manager. It's helping do the work of the manager. So in the example that I have here, we are doing pronated curls. So too short for this. A pronated curl is, in a typical curl, your palms up. In a pronated curl, your palms down. Okay, so when I'm doing a pronated curl, like this. Again, I'm flexing the elbows. The main activator here is my biceps brachii. But I'm going to have assistant muscles, and one of those assistant muscles is on the side of my arm and kind of underneath the bicep, and it's called the brachialis muscle. So we're going to pull up, and that's going to be my curl. That's one of my assistants there. The pronator teres is also an assistant here because we are doing pronation. Now, regardless of what type of curl you're doing, when you're doing it, if you want to do it effectively, you need to keep your elbows in and your shoulders should not move. If you are doing a bicep curl and you're doing this, unless you're doing like this is your action. If you're just trying to do a basic curl, if you're swinging or you're using your shoulders to really lift the weight, like you're shrugging your shoulders, you're not isolating the bicep. You're using the stronger muscles. That's a very common thing to happen in strength training as we're learning how to do the moves, because we're training muscles that are weaker and we're going to have stronger muscles that are going to want to pick up the slack. But if we wanted to isolate during my pronated curl, I need to keep my scapula still. It cannot move because that's the origin of my bicep. I don't want it to do anything weird. So what's going to happen in this particular instance, we have a fixator. A fixator will stabilize the origin of that muscle so it stays put. In this case, we're using the deltoid as a fixator, so that as you're doing that pronated curl, your scapula is remaining in position, and you can actually feel your anterior deltoid kind of kick in when you're doing this correctly. So all of these different muscles are used just to do a simple curl. So it's not just the bicep doing it. That's kind of the theme that we're getting at. Okay, a couple more things. First off, this is going to help you with lab. Every muscle we're learning, and we're not learning that many, their names will give you a clue to something. What it looks like. Rectus, straight up and down. How big it is. Maximus, large. What's its shape? Orbicularis, it's going to be circular. Piriformis, it's going to be pear-shaped. Sometimes they'll tell you what they do. Flexor digitorum superficialis. That actually tells you what it does. It's going to flex the digits, and it's the most superficial in the forearm. How many origin sites does it have? Triceps, 3 origins. Where it's located, occipitalis, frontalis, zygomaticus major, mentalis. They tell you where they are. And then we have the special ones like the sternocleidomastoid that tell you they are going to come from the mastoid process down to the sternum and clavicle, which just so happen to be the origins and insertions. So one of the things that I recommend students do in lab is they take note of this. What is this muscle trying to tell me so that it can help me out? So let's talk about moving forward. We have 3 more videos to watch. They are all going to be divided based off of regionality, which is the same order of introduction we're going to see them in lab. So the next video you're going to see, we're going to talk about the head, neck, trunk muscles. Then we'll talk about the muscles of the upper limb and the muscles of the lower limb. Here's what we're focusing on again. Regionality. How are the muscles working together? Is there a common action, a common origin, a common insertion? Why are they built the way they are? You only need to know the specific muscles that we discuss in lecture. Again, in lab, you're going to get a list of about 100+ muscles. We are not responsible for that in lecture, just the ones we talk about, because the ones that we're going to be talking about are going to apply to things like dental hygiene, nursing, and physical therapy, so that you guys can get an understanding of like why we are even learning this muscle. So I hope this helps you guys, and I will see you in the next video.